Everyone. Thanks for coming to the TAMIDS seminar session this week. And actually, it's my personal pleasure to have Professor Vikalo to present a seminar this week. And Professor Vikalo actually got his PhD degree from Stanford. And actually, we got to know each other because both of us having doing signal processing and their implementation to bioinformatics. So he has been in, he was in Caltech, actually applying compressive sensing to developing new high throughput molecular profiling biochips. And recently has been developing lots of fantastic signal processing, machine learning methods for say communication systems and also bioinformatics systems. And today, actually, he's not going to talk about bioinformatics. He's going to go back to our home electrical engineering and trying to develop some optimization methods for sensing and learning systems. And without further ado, please, Professor Vikalo.
Thank you, Chang-In. Thank you for the kind introduction, and thank you very much for inviting me. It's unfortunate that we couldn't do this in person. I would have loved to visit the campus and spend some time there. Hopefully things go back to normal and there are opportunities to visit in person sooner rather than later. So let me try to share my screen, and please let me if you can.
It's good.
See it. All right, so view. All right, so as you could tell by the title of the seminar, today I will talk about two related but nevertheless distinct topics and ultimately research efforts that are connected through the common concern about systems that are operating under resource constraints. And the exact nature and severity of those constraints may differ from one application to another, but basically they arise in a form of power constraints, and by that I mean both battery as well as compute power. And communication bandwidth constraints, especially on the uplink of various distributed systems. So the first line of work is going to be focused on large-scale sensor networks and selecting and collecting informative information there. And the second one is going to be shifted towards distributed collaborative learning systems and resource constrained issues that come up in those. A common thread in our approach to tackling resource constraints in these problems is going to be a formulation as a subset selection problem, and essentially coming up with efficient ways to solve subset selection. To perform subset selection. So as I was saying, the first line of work that I'll present is focused on measurement selection and information gathering in large-scale sensor networks. So think of a setting in which a potentially large number of sensors that operate under power constraints are observing their environment and are transmitting either their raw measurements or a summary of those measurements to a central location, to a sensor fusion or fusion center rather. And then this fusion center has basically two tasks. One is to use the received information to come up with estimates and track various objects of interest from the environment, objects like quantity that characterize the environment, and simultaneously take into account that the communication bandwidth, uplink communication bandwidth that the sensors have available is limited, and therefore perform selection of the future measurements to be collected, future sensors to be activated, so that overall communication bandwidth is conserved, while the informativeness of the collected information is maximized. And what exactly I mean by this informativeness will hopefully become clear as we proceed. So that is one or the problem that we'll consider in the first part of the presentation. In the second one, as I already said, we're going to shift our attention to distributed learning systems, in which a collection of users collaboratively train a machine learning model meant to tackle a particular task of interest. And we will specifically focus on the recently proposed federated learning systems that have received a lot of attention. So these systems are motivated more by privacy originally, because they aim to target the setting in which each user has access to some local data, which is typically private and personal, and is unwilling to communicate that data to the cloud, to some central location. To that end, each user, each client trains a model locally on their private data, and then communicates only the model or the updates of that model to the cloud. So privacy, as you can tell, is meant to be provided by design, just by the virtue of not communicating the data itself, rather only the models are communicated. Nevertheless, while the privacy is primary concern for this scheme, there are clearly communication issues that come up as the size of these models may be considerable. And lately, there has been a lot of effort on trying to judiciously either sub-select clients that would communicate their model updates, or to in some way reduce the size of the model. So that's going to be at the high level subject of the second part of the presentation. So here's a formal organization of the talk and the flow of the topics. In the first part, I'll talk about remote observation, selection, and information gathering. And this line of the work is going to be formulated very much as a model-driven problem. By that I mean mathematical model driven problem, and there will be some theorems that I will just state, so that there will be some theoretical results as opposed to the second part of the presentation. And I'll first talk about linear models and observation, selection, and gathering in those settings, where we will rely on the concept of submodularity to optimize, to select the most informative measurements where the informativeness is with respect to the MSE criterion. And along the way, we will make an observation that as the size of the networks increases, the existing methods that are efficient in relatively small to moderately sized sensor networks become prohibitive. And to that end, we will propose and analyze a new algorithm that relies on the established submodular properties of the objective to efficiently collect data, and we'll talk about some performance guarantees of these proposed methods. Then we will move beyond linear models that are often coming up in various applications, such as phase retrieval and many others, and talk about extending the previously presented ideas to this setting. And for that, we'll we'll rely on certain concepts from estimation theory. Specifically, we'll see how to exploit the so-called Ventries bound, which is Bayesian version of the Kramer-Rao bound, and use it to perform observation selection in quadratic models. Then in the second part of the talk, we'll move to the a little bit more data-driven set of problems, and talk about another subset selection problem, but now in the context of selecting clients in federated learning systems. By the way, please, if in case of any questions, please feel free to interrupt me. I should have gotten used to it by now, but I'm still struggling to pay attention to chat. It's whatever happens there is often lost on me. So if there's anything that you'd like to address as I proceed, please feel free to interrupt me. All right, so on to the first topic, and let me start with an illustrative example of a large-scale sensor network, which is going to be for us a swarm of UAVs that are collecting remotely information about target or multiple targets, about their positions, and then conveying or transmitting that information, those measurements, to a remote control unit. And then this control unit is running schemes that are determining locations or estimating the precise locations based on the collected measurements, and also attempting to subselect sensors that would provide in the next rounds of the estimation the most informative measurements. So the goal is to come up with computationally efficient ways of measurement selection, where the again goal where the criterion is going to be the often used mean square estimation error criterion for the accuracy of the target tracking task. All right. So as I said, the first line of work is very much model driven. So let me start with a dynamical model expressed in form of a state space model. It's either inherently linear or linearized, which that's something that I will address shortly in when we move on to the more complex, nonlinear schemes. I'll address this issue of linearization and what we may potentially lose by doing that. But for the time being, let's assume that the model is dynamical model is linear. So we have our standard state space model where we are interested in tracking the state vector xk based on the collected measurements yk, and we're assuming Gaussian noise for the time being with covariance, well, Gaussian state and measurement noise with covariance matrices Q and R. So if we had no concerns about communication resources, a classical Kalman filter would provide optimal state estimate, optimal in the mean square error sense. However, because of the communication constraints, we are interested in subselection of sensors in each step k. So at each time step, out of n measurements, we subselect capital K to form a subset S sub K. And we're going to assume that the control unit is now tracking the state vector based on a Kalman filter by incorporating only the communicated measurements, so measurements that have been pre-selected and placed in this subset SK. So what are the metrics that we use to measure quality of our estimate? We're going to use ultimately mean square error, but the objects that help us compute that are predicted and filtered error covariance matrices. So we're considering the so-called Schmidt's version of the Kalman filter with the time and measurement update step. So every time you receive a measurement, you perform measurement update, and the quality of your estimate is captured by the filtered error covariance matrix. And after that, you sort of let the dynamics of your system take your prediction one step further, and the quality of that prediction is characterized by the predicted error covariance matrix. So with no communication constraints, this would be pretty standard. Difference now is that due to limitation to only a subset of measurements, during the measurement update step, only those measurements are used to perform the measurement update, and that has percolated and has affected this expression for the filtered error covariance matrix. So SK shows up here because, well, these are the measurement matrices that have been compressed so that only those rows that correspond to the selected sensors are present in those compressed matrices. So as I mentioned already, the criterion that we're interested in is the mean square error. And that is basically the trace of the measurement covariance matrix or filtered error covariance matrix. And the task that we're interested in solving is minimizing this object as a by performing selection of K most informative sensors. For convenience, we replace the filtered error covariance matrix by the inverse of the Fisher information matrix, as for reasons that will hopefully become obvious shortly. All right, so challenges here are fairly obvious. This is a combinatorial problem that has been shown to be NP hard. And due to the high complexity of solving this optimization, people tend to resort to various approximate methods. Nevertheless, even with the use of those approximate methods, as the size of the network scales up, as the size of the network grows, there's need for being able to come up to solutions to this optimization problem with even improved efficiency. So just a quick overview of the existing approaches. Some of the first approaches to this sensor selection problem in the specific context that I described have been relying on essentially optimizing the volume of the confidence ellipsoid, which is basically log that of that filtered error covariance matrix. And perhaps the first work that considers the sensor selection problem in precisely this setting that I described relied on semi-definite relaxations in order to solve it. But soon thereafter, it's been observed that this log that objective function is what's known as submodular. So I'll formally introduce that concept in a few minutes. And then, a number of variations on how to tackle the problem that rely on good properties of submodular functions followed. Again, the reason for going after log that objective, it's interpretable. The minimization of the confidence ellipsoid, but primarily, in addition to being interpretable, or perhaps primary reason is it's convenient. It is an objective function that has very nice properties that can be exploited to come up with fast algorithmic solutions. But the trouble is, or the downside to going with log that as your objective function is that it is not as explicitly related to the mean square error, which is often the desired objective. Nevertheless, people have attempted using greedy approaches directly on objective functions that relied on mean square error, even though which was sort of predicated on the conjecture that mean square error has similar properties as log that. However, as it can be shown, mean square error, the trace of the filtered error covariance matrix, is in fact not submodular. It is, as we proved, weak submodular. And greedy method does not come with conventional performance guarantees that tend to characterize the greedy schemes applied to submodular optimization techniques. The other downside of using plain vanilla greedy schemes is that, as I'll argue later, they are not suitable for large-scale networks, or as I will demonstrate on some concrete examples, they're not suitable for large-scale networks. So our work attempts to tackle both of these issues that I've been implying. The first one is that it is desirable to tackle the objective function closely related to the mean square error. That's one, and the second is we're going to show how to improve the computational efficiency without sacrificing much in terms of the performance, in terms of the accuracy. So to this end, we'll show that the mean square error criterion is actually what's known as weak submodular, and we will propose a randomized greedy scheme that by relying on submodularity or weak submodularity can be analyzed, and we can provide some formal performance guarantees that such randomized greedy schemes achieve. In practice, they tend to demonstrate near optimal performance. All right, I keep bringing up this concept of submodularity, and perhaps not everybody in the audience is familiar with it, so I should really define it. So submodularity is property of set functions, and set functions are any functions, as the name suggests, that assign a value to subsets of a ground set. So, for instance, if you have a set of networks, a set of sensors in a network, then a set function would be a proper function that for each subset of sensors assign a specific value. Just for a variety of examples, here's an illustration of a set function on an undirected graph, specifically the value of a cut. So the value of a cut is defined as the sum of the weights on the edges that are cut, that are enclosed or crossed with a cut. And there are many obviously discrete optimization problems in which set functions will play a major role. We say that the set function is monotonic if as you increase the size of the set, you increase the value of the set function. So if set S is a subset of T, then the value of function evaluated on S is smaller, well, less or equal than the value of the function evaluated on T. And both S and T are subset of the ground set X. So that's, you know, semi-formal introduction of set functions. But now, as I started this on discussion on set functions, so submodularity is a property of set functions that says something about the marginal gain. So what's a marginal gain? Marginal gain is essentially the delta in the value of the set function that you get by incorporating an additional element to the set. So specifically, marginal gain of incorporating element J into the set S is the difference between the value of the set function on S union J and the value of the set function on S. So finally, on to the submodularity. Submodularity is a property of set functions. If a set function satisfies submodularity, then essentially it has diminishing returns. This incorporation of elements has diminishing returns. That means if you have two sets, S and T, as illustrated here in the figure, adding element J to T has smaller marginal gain than adding element J to S. So you get less bang for a buck if you incorporate element in a bigger than if you incorporate it into a smaller subset. Again, S in all this, S has to be a subset of T. Now, submodularity has very desirable properties when it comes to solving various subset selection problems, and for this reason, people try to extend it so that the same framework could be perhaps applied to set functions that, loosely speaking, somewhat weakly violate this diminishing returns property. So that led to several definitions of so-called weak submodularity, and we're going to focus on one that relies on so-called curvature of the function, and goes as follows. We consider the same sort of diminishing returns property, but modified slightly by allowing this allowing this bound on the right-hand side to be scaled by a certain number, by certain constant capital C, which is the element-wise, called maximum element-wise curvature of F. So that basically means if you add an element to the set T, the benefit of it is no more than C times the benefit of adding it to a smaller set S. So clearly, if C is equal to 1, or if it happens to be smaller than 1, then we have a submodular function, right? So the condition for a set function to be weak submodular is that C can be bounded above by a finite number. Okay, any questions about this, about the setting these concepts of submodularity and weak submodularity? Okay, if not, then let's go back to what we're trying to do. So we're going to define set function f of s in these as shown here. So this is the Fisher information matrix that's associated with some selected set of sensors, capital S. And if you think about it, the trace of this difference is a meaningful thing to consider, because it tells you what is the gain in the quality of your estimate in terms of the achieved mean square error that is obtained by incorporating measurements of the sensors that are placed in set S. Remember, this was the error covariance matrix after the time update, so it's predicted error covariance matrix. So that predicted error covariance matrix is reflective of the error after the time update step. So that error is reduced after you incorporate the new measurements, after you apply the measurement update step in the Kalman filtering procedure. So this essentially tells you, therefore, how much you reduce your error by incorporating the selected measurements into your estimates, right? So therefore, it makes sense to consider the problem of maximizing this, information gain by selecting the subset of sensors. So that is basically the constrained optimization that we consider, and this is completely equivalent to the previously stated task of minimizing the mean square error. All right, so here are a couple of useful information before we proceed. So this function f of s is clearly monotone. The more sensors you incorporate, you're going to get higher values of this object, meaning you're reducing the mean square error further as you incorporate more sensors. And critical for the computational efficiency of sensor selection is an expression for the marginal gain that you remember I defined a couple of minutes ago, which is the gain of incorporating sensor J into your selected set of observations. Those of you who are intimately familiar with the Kalman filter will find that this might resonate with something called sequential information processing in Kalman filters. Just as a side remark, when you have large matrices and you want to avoid inverting them, instead of running the conventional Kalman filter, you may incorporate measurements one at a time, and that leads to so-called sequential information form. And this is basically something very, very similar and very useful when we're going through this sub-selection of the sensors and their sequential incorporation into the overall estimator. All right, so here is a summary of our main theoretical results, and I'm not going to, of course, not going to show you any formal statements, formal theorems. They're a bit cumbersome. If anyone is interested, they are in our recently published paper that just came out earlier this year in Transactions on Automatic Control. That basically say that this function f of s that I just defined is not submodular, but it does have bounded maximum element-wise curvature, which means it's weak submodular. So under which conditions this is true? We consider both the deterministic and probabilistic case. Deterministic case, if you if the maximum, if the largest eigenvalue of this object H transpose H satisfies certain bounds, then that one can establish a deterministic bound on the maximum element-wise curvature. Probabilistically, if the entries in the measurement matrix are IID with bounded variance, we come up with probabilistic guarantees probabilistic guarantees on the value of the maximum element-wise curvature. Skipping again, as I said, formal statements, I just want to point out the intuition, and it goes as follows. The objective function, this sort of function that measures information gain, is going to be weak submodular as long as your time step doesn't take you to the direction in which the time update covariance matrix becomes ill-conditioned. So this is a matrix that may go rampant as you're waiting for measurements to arrive. So if it becomes ill-conditioned, then weak submodularity may end up being violated. But if it remains well-conditioned, then the curvature of f of s will be small. So this is again just establishing fundamentals of fundamental property of the objective function that we are aiming to optimize for. But that brings me to the next step, is that even after having established weak submodularity, the question remains, what do we do when the network becomes large? So I mentioned several times greedy algorithm repeatedly. I brought it up. I haven't really described it intentionally. I wanted to describe it in this context. So greedy does something very, very simple. Basically, it goes through all the sensors, finds the one with the largest information gain, and adds it to the set of selected sensors. Then with this sort of seed, with this configuration of the selected sensors, you revisit the remaining sensors, you pick the one that gives you the largest marginal gain, and you keep going until you hit K, which is the bound on the size of the set that you're selecting. So what we're proposing is a modification that essentially, instead of looking over entire set as it's going, making the choice about which sensors to include, randomly without replacement selects a subset of sensors and does the search only over those. And clearly this is going to work only if, well, I mean, this is going to work as well as, we'll see what kind of guarantees we can provide. But this will not lead to a major deterioration of the performance of the standard greedy if this randomly generated set overlaps with the optimal set of sensors. So motivated by that idea, we analyzed the size of this randomly generated set, where we scaled it according to this. N is the number of sensors, K is how many we select, and then we use this parameter that controls the size of the search space. So with such a choice of the size of the random set, we essentially run the scheme that I just described, and I'm going to skip through the details. Just get to the what are the interesting results. We can show that on expectation, your solution, well, the utility function, our essentially the information gain that we get from selecting a set of K sensors is not going to be too far off from the utility function of the optimal set. And how far off is going to be is this multiplicative factor here. Just to parse things out, if any of you who are familiar with submodular optimization and greedy algorithms may recall that the multiplicative factor there is 1 minus 1 over E. Weak submodularity and randomness impact that 1 minus 1 over E in two ways. The weak submodularity is captured by this coefficient C, which is greater or equal than 1. It's equal to 1 when the objective function is submodular. It's greater than 1 otherwise. And this beta is what captures the fact that we're randomly subselecting sensors rather than searching through the entire set of sensors. So in a limit of not subselecting, but using all the sensors and the objective being submodular, we would be left with just 1 minus 1 over E. So this sort of nicely shows the impact of both weak submodularity, so deviating from the standard submodular condition, and randomness added to the search procedure. Interestingly, also we can bound the expected mean square error that we achieve by performing randomized greedy search, and it's nicely captured in terms of the mean square error of the achieved by picking the optimal, so not greedy, but optimal obtained by solving the original combinatorial problem set of sensors. And it's a function of the predicted error covariance matrix. And running time of the algorithm is reduced by a factor of k compared to the greedy scheme. So we've ran a number of simulations comparing the performance of the scheme with a greedy algorithm. So this is in the context of multi-target tracking. As one can show, and I'll just sort of quickly breeze through it. The accelerated algorithms obtained by randomly subselecting a set of sensors before greedily searching through those subselections improve speed-wise considerably over the conventional greedy scheme, while their performance really doesn't differ all that much. And the difference in performance is shown here through the root mean square error. So this is the performance of the greedy and proposed modifications. The accuracy has really not changed much. What I'm showing is root mean square error is a function of the scale of the system. We're scaling system up to, starting from 200 sensors up to 4,000 on the right side of the plot. While the running times are improved by a factor of up to 30 by going with the randomized greedy as opposed to plain vanilla greedy. Any questions?
Can I ask a question here?
Sure,
I assume that you are going to finish the first part. Right, so you mentioned your probabilistic bonds with a random measurement matrix H.
Right.
So I assume that in your state space model, you assume all the noise covariance matrices are fixed.
Yeah, or we're learning them at the central site in some way. Yes, yes.
But the result, I mean, for the theoretical results, do you need them to be like a fixed, or you actually can accommodate the potential noise or uncertainty on those things?
We assume that they are, they are allowed to be time varying, but we do assume in the statement of the result that they are known. So we haven't explored the impact of the noise in those parameters. That's a good point.
I see. Great, thanks. And also, we have like 10 minutes.
Just I'll speed up. I know.
Thanks.
No worries. I noticed that I'm going slower than I had hoped for. So let me then just sort of breeze through the rest of the first part and move to the second. So this is all fine and well, but it's constrained to linear systems. In practice, we often have models that are nonlinear, and the quadratic models often come up in problems such as phase retrieval. Even this multi-target tracking in its original form is nonlinear, specifically quadratic, and these linear models are obtained by means of linearization. Linearization, however, while an efficient way, a convenient way of simplifying the model, leads to the setting where the performance guarantees that you get don't really apply to the original model, right? I mean, they apply to the linearized model. And motivated by this, we've considered a family of quadratic models that come up again in a number of applications. And what we did, I'll skip the linearization approach that is part of the existing work. What we rely on in this work is that these nonlinear models typically lead to biased estimators, and we rely on the so-called Ventries bound, which is a clever extension of the Kramer-Rao lower bound to essentially, settings in which estimators are allowed to be biased, and it's can be interpreted as a Bayesian version of the Kramer-Rao bound. It's expressed in that spirit. So what we were able to do is for quadratic models, we computed the the Ventries bound in a closed form, and then used it to formulate the metrics, performance metrics that are closely related to the basically mean square error of your estimator. So we have formulated again objective functions that rely on the Ventries lower bound in the spirit of attempting to in the case of unbiased estimators to minimize the Kramer-Rao lower bound. Here we're minimizing essentially the Ventries bound. And what allowed us to do that efficiently is an observation that this objective function is in fact weak submodular. The function, the objective that I just mentioned and formulated. So what's interesting, I'll just take you to this slide, that the benefits of using this approach through minimization of the Ventries bound becomes very, very explicit when you compare it with linearized model in, say, this multi-target tracking application that I was talking about before. So by minimizing the Ventries bound based objective function as compared to the MSC of the or trace of the error covariance matrix of the linearized model, what we observed are significant performance gains. So let me then stop here for when it comes to the first part. I'm sorry, I'm clearly running very late, but are there any questions on this?
Hello.
Yes, please.
So when we talk about this Ventries bound, it will depend on the bias.
Yes.
Right?
Yes.
So when we compare to the linear models versus the quadratic model, so the bias for these models could be different. That could cause a different in objective, or is it like you have mean square error? So bias is also part of that mean square error, right?
Right. But again, what we're optimizing for is this criterion that is basically a combination of the Fisher information matrix and the Ventries bound. We don't explicitly study the bias. What I'm showing you is the actual mean square error of the estimate.
Okay.
But yeah, I mean there's certainly the bias that impacts the expressions for that come out of the Ventries bound.
Good. Thank you.
Sure. All right. So for the second line of work, we're moving to distributed learning systems, and specifically federated learning, in which a number of clients attempt to learn a certain machine learning model or model to perform certain task from their own local data. And they do this in a number of cycles in which they train locally, form updates that are then communicated to the server, which agglomerates in some way, for instance, by plainly averaging or doing something more sophisticated with the received models, and then broadcasts those models back to the clients. So the challenges that arise here are numerous. The number of clients is large, potentially in millions. You often don't see a client that contributed a model for a long time, if ever, again. And the models that are being communicated may end up being large, with a lot of parameters. And the systems are changing dynamically, which means new users may join in, new data is generated by old users. And this leads to generally potentially large number of rounds. So there are many different issues that come up. We're focusing on one specific, which is the communication efficiency on the uplink, and trying to reduce the amount of communication from clients to the cloud. And there are two lines of work that are complementary to each other. One is focused on reducing individuals' communication by compression, sparsification, and so on, just reducing the amount of data that is used to represent the model. And the other one is by performing client subsampling, or identifying clients whose updates may be the most informative. So it's the second line of work where our work in progress falls under. So I'll just explain the main idea. It is predicated on or it's building on an observation that the stochastic gradient descent, which is or an optimization technique used to perform model updates, can be interpreted under certain conditions as discretization of an OU process, Ornstein-Allenbeck process, and this has been reported lately by a number of people in the literature. So essentially, you interpret the weights or progression of weights of different clients' models as realizations or basically sample paths of some underlying OU process, which just loosely speaking, is a stationary process which over time drifts to its mean function. So this is a formal definition by means of a stochastic differential equation of a OU process, and weights in this context are interpreted as the samples along the sample path of the process. And the idea that we have is pretty simple, basically relying on the proximity of the sample path to its steady state, decide whether or not the model update is worth communicating to the server. So this is, you can see connections to a couple of things here. The notion of remote sampling of random processes, which has been studied extensively in literature over the years, and sort of building on the ideas established there, one can actually formally claim that it is the optimal scheme is based on a specific form of thresholding. So the thresholding that we rely on is essentially the thresholding the magnitude of the update that each client computes locally. So each client that receives requests for an update trains locally, computes the magnitude of the its update, and compares it to a threshold that it has received from the server. And based on the comparison with this threshold, decides whether or not to communicate the model upstream to the server. So this leads to a small modification of the scheme that already exists that's used in practice. So the server still selects a certain number of clients, but in addition to the ping, it sends them, and in addition to the model that it broadcasts, it sends them threshold. And as I was already saying, the individual clients then compare the magnitude of their update to the threshold and decide whether or not to communicate. However, they always do communicate this magnitude of the update to the client, to the server, because the server is going to use those magnitudes to compute the new value of the threshold in the next round of the training. So I'll just show you some of the results and compare in comparison to the previous existing methods. So prior strategies were very, very simple. So one strategy would essentially, for all the clients that decided not to communicate by performing some decision in place of the models that did not arrive from those clients. The server would use the initial model. So you're essentially you have a sort of a damping term when evaluating the new model because you're using for a number of clients that did not communicate what they started with. Another strategy is, we're referring to it as zero strategy, is basically more aggressively simply dismissing all those clients who did not communicate any updates and form the new model based on only the updates that it did receive. So there is a subtle difference between the two, and clearly the first one is going to be a little bit more stable as our empirical results confirm, and will experience less variations. So I'll as I said, we did quite a comprehensive study of the performance of these different methods on different sets. So these are results on eMNIST, which is federated learning, a friendly version of the conventional MNIST data set. Shakespeare data set that's convenient for testing text prediction applications, and based on an image data set, CIFAR 100. Our observations consistently have been that among the schemes, the one that we propose appears to be the most stable in terms of the variability of the model and speed of convergence. Ultimately, in many settings, all of the methods tend to apply close to each other, but how they get there, the stability differs. We do have some interesting, semi-interesting theoretical guarantees when it comes to the variance of the method that we developed, specifically in comparison to the both zero and ignore variance. So zero strategy, the one where you essentially use the previous models to represent users that did not communicate, is affected by bias. Ignore strategy is affected by high variance, and we're actually able to show that analytically that our proposed scheme is preferable in terms of those two metrics with respect to the prior methods. So in the interest of time, let me just sort of summarize the contribution of this part. We propose a new way of selecting clients in federated learning systems. I should say that we, in addition to this, we explored that other dimension. If you remember, there are two ways in which one can tackle this issue with large communication demands. One is by compressing the model. Well, one is the one that we explored, selection of clients. The other one is model compression. So we investigated whether these can play together well with our scheme, and we observed consistently that we can achieve up to 50% reduction in communication on top of what's provided, what's accomplished by the schemes that perform model compression. I'm happy to talk about that offline. As part of ongoing and future work, we are investigating these client sampling or selection ideas as a way of perhaps promoting fairness in federated learning systems. So let me stop at this point. I apologize for going over time, and I'll be happy to take any questions.